So the last part of this section is looking at variance and standard deviation. And we've already talked about these things as a way to measure how far out or how spread out data is. Now, the actual definition of variance is right here. It is the arithmetic mean of the squared differences between each value and the mean value. Whew. That makes total sense now, right? So we're going to look, what does that actually mean? And why is it set up that way? So we're going to look at it a little bit more in detail than what we did before. Before, we just learned that variance and standard deviation told us how far data was spread out. When we did our probability, we learned that if you have a normal distribution, that you go 3 standard deviations above and 3 standard deviations below, and you have almost all the data that's possible. So here we have 2 tests. I could get you to type all those values in and find your mean and standard deviation, but that would just waste our time a little bit. So if you put this data into your calculator and found the mean, calculated the median, looked through the data to see which one happened the most, and figured out the range from the smallest to biggest, those would be the numbers that you would get. If you did the same thing for the second set of data, everything is identical except for the range. As I was thinking about this example, I could have changed a couple of other things in here and even had the range to be identical. So we have 2 different sets of data, but they're very, even though the median, the mean, and the mode are all the same, they're very different. Can you see that test 2, everybody is closer together? And in test 1, things are more spread out. Now that can be seen in the range, but another way of looking at that is with our variance and with our standard deviation. So if we make frequency tables for each of these, this is what we get. Again, we can see that in the second one, everything is more grouped together, so that already shows us a little bit more. But we're going to look at the variance and the standard deviation to see how that is a different number for each. Okay, so here is a big chart of values. In this big chart of values, this is our first test. We've got those scores from 5 to 20 listed and the frequency of each one. And there was 32 scores in total. This fx is just your mark multiplied by its frequency. So here the 7 has a frequency of 2, so that's why that's 14. And the 9 has a frequency of 2, so that's 18. Now to calculate the variance, so if we go back to that variance formula, the variance, it is the arithmetic mean of the squared differences between each value and the mean value. Okay? The squared differences between each value and the mean value. Well, first of all, if we find out how far away is our score from the mean. So we had calculated that the mean of this data was 13. So when you get a score of 5, does it make sense that that's 8 below the average? And your score of 13 is right on the average. And if we look down here, 18 is 5 above the average. So we remember that our mean in this case was 13. So what happens is you have some values that are positive and some values are negative. Now if you want to find out how spread out data is, and you have some values that are negative and some values that are positive, and you try to combine them together, they're going to cancel each other out. So the way that variance is calculated is that those differences are all squared. And by squaring those differences, we get all positive numbers. And if you would add up all of those numbers, the bigger the number you get, that means the farther away things are from the mean. And the smaller the number you get, the closer they are to the mean. So we square all these differences, and then again, since 7 happens twice, you would multiply that squared difference because it happens twice. And you add up all of those squared differences. In this case, it's 616. And if you divide that by the 32, right, their mean was 13 still. If we divide that 616 by the 32 numbers we have, that 19.25 would be our variance. And then the square root of our variance is our standard deviation.
Lindsay to the office, please. Brett Lindsay to the office.
So again, the notation in here, we've got the sigma sign for sum. Here's all of our frequencies of each individual one multiplied by the square of the difference between the value and the mean divided by how many you have. Now this formula isn't on your formula sheet because for the most part we're always going to calculate standard deviation and variance with our calculator. But it's important to understand where it comes from, and you can see why if things are further spread out from the mean, when you square them and you get a positive number, that really makes a difference for the calculation of that value of variance and standard deviation. And so now if we go back to that definition that we underlined before, arithmetic mean, that means it's the average. That's why we divided by 32 at the end, because we had 32 items. Of the squared differences, so we find the difference between the average and your score, square it, and add all of those ones up, and divide by how many we have. So looking at our chart again, take a value like 10. 10 is 3 away from the average. You square that, you get 9. Since 10 happened twice, the total would be 18 for the tens. Add up all these square differences, divide by how many you have, and that's your variance. And then, of course, your standard deviation is just the square root of your variance. Do that same thing for test 2, and you would have found out that its standard deviation is 1.77. So a significantly lower number for standard deviation for that one. And we could see that because everything was much closer and much tighter for the mean. So on your calculator, there is a sigma x and there is an SX. For this course, we're going to be using the population standard deviation. When you get into university and you start looking at different things in statistics, they're going to also look at sample standard deviation where you divide by n minus 1 instead of n. And so there's reasons for that. It's a better representation of the population when you're using a sample that way. But we're going to use the sigma one on our calculator, and we're going to use the population standard deviation. So with this one, I'm going to get you to do some calculations here. I'm not going to get you to count out all the frequencies. I'll give you that. I'd like you to calculate everything else and fill in the chart and find the variance and the standard deviation by hand. Once you're done, take out your calculator, put the workers into list 1 and the frequency into list 2, and check if your number is correct. All right, I'll put up the rest of these values so you can check. All right. So, a low standard deviation, here are our normal curves from before. Our low standard deviation means everything is close to the mean. Our big standard deviation means everything is more spread out. Remember from probability that the area under the red is 100%. The area of the yellow is 100%. So when you have a normal distribution, the area under the curve represents the percentage of people that would occur for. And so the whole thing is always 100%. So as soon as you get a low standard deviation, things are closer to the mean, well, that'll mean your normal curve will be higher. And a high standard deviation where things are spread out, then that curve will be lower. Some properties of standard deviation. Because we're adding up those squares, your standard deviation is never negative. If you have an outlier in your data, it can really, really, really affect your standard deviation. So that's why sometimes outliers are not considered part of the data. So the bigger things are spread out, the bigger your standard deviation. And if all the values are the same and there's no variance in your data, all your scores were 50, then the standard deviation would be 0. So sometimes what happens is we see on exams sort of conceptual things like, what would happen if you added 15 to all your data points? And they said, your mean was this, your median was this, your standard deviation was this. They give you those values. Then each of your points, 15 was added to each of your points. How would each of those things be affected? Would it make sense that your average would go up 15? Would it make sense that your median would go up 15? Would it make sense that your standard deviation would stay the same? Because that whole normal curve just got moved over here, but it didn't get wider or narrower. Now, if you multiplied or divided everything, so you have all your data points, you decide to multiply them all by 5, can you see that your maximum would go further this way and your minimum would go further that way, but your mean would stay the same? Your average would stay the same, but now things would be much more spread out. In fact, your standard deviation would get multiplied by 5 then as well. So sometimes you'll see these sort of conceptual types of questions asked of whether or not you understand how mean and standard deviation work.